Welcome everyone to our solar photovoltaics course. Today we have 8th week, the first module. So far we have been discussing about the different technologies of the solar cell. In our class we have talked about silicon solar cell, we have talked about organic solar cell, perovskite solar cell as well as quantum dot solar cell and nanoparticle based solar cell. And when we have discussed this all different kind of solar cell, so the fabrication, the technology of making the solar cell, and we have seen that most of the solar cell has one thing in common, they have a sandwich layer between two electrodes, one is a photoanode and another is a cathode. Now, in most of this case this cathode material is a metal electrode like platinum or like aluminum or some kind of like gold, silver we use as a counter electrode or metal electrode. Now, this metal electrode they are deposited in a special environment, they are not deposited under the ambient condition. We need a high vacuum or devoid of any gas molecule inside the chamber to deposit these metal atoms on the top of this solar cell. Now, this special environment or what we call as a vacuum environment, that requires a special kind of instrument setup or special kind of chamber to create or to make that kind of condition. In today's lecture and some subsequent lecture, we will learn about this vacuum technology, what is the meaning of the vacuum, what do we mean by high vacuum, low vacuum or medium vacuum, and how we can make the vacuum chamber. So, the idea of the vacuum technology that is way back to 17th or 18th century or even before that. But in the first hand we need the question like why we need the vacuum or what do we mean by the vacuum. Now, let us look at this figure here, like you consider an arbitrary circle like this and which has been filled with some blue color solid bubbles. So, let us consider this spherical shape is like a chamber and this blue color dots they are like the gas molecule. Now, look at the second picture here, the number of the gas molecule or number of the blue solid sphere in the second picture is less than the first picture. Now, you look at the third picture here, here the number is much less in comparison to the first thing. So, by in some system to begin with a crowded number of atoms, if we start getting rid of one by one atoms or if we rarefied the systems, so finally we can achieve a system where the number or the density of the gas molecules or the density of the atoms of the gas molecules in a particular volume is much reduced in comparison to the first case. Now, what will happen, let us say we want to move a particle in a straight line over a large distance. So, in this case if I have to move the particle along this distance, so this particle has to collide each and every time with this blue sphere. But what happens here, you can imagine the number of collision is much reduced in comparison to the first case. Now, you come to here, the probability of collision is very less in comparison to the first and the second case. So, that means now let us consider a practical case. I have a source of the atoms at this side and I have a target on the other side. Now, I somehow by some means I have heated this source so that I can generate a vapor of the atoms or atoms. So, these atoms will go in a straight line. Now, while travelling along this chamber, if it is suffers multiple collision, then its paths will be deviated and it will not be able to reach to the target substrate. So, if I wanted to have a very uniform coating on the target substrate of our vaporized atoms, so what we require as less of the interfering atoms inside the chamber. So, to make it as less interfering other gas molecules inside the chamber, we need to create the vacuum. So, in our atmosphere we know that there are different layers is there and we call it as like troposphere, stratosphere, ozonosphere, ionosphere, etc., etc. Now, if we go above and above, so what will happen, the pressure and temperature changes and the effective density of the gas molecule also changes. For example, like whenever any kind of radiation has to pass through the atmosphere, we know that they has to pass through the cloud, I mean which contains the condensed water and different kind of gas molecules also. But if I have a like high vacuum surface, so then if I want to deposit some kind of gas molecule on that, so I do not want like lot of the other molecules to interfere with my systems. So, I want a very clean substance, and to get a clean substance or a clean surface, I do not want any interfering things inside my systems, and that is why we need to create the vacuum. So, by definition, an ideal vacuum is a space devoid of all matter, does not exist even in outer space. So, it is not possible to have a space completely devoid of any matter. So, it is a very ideal hypothesis. So, in real case what we talk about is the partial vacuum. So, the actual vacuum is actually partial vacuum, a space containing gas at a pressure below the surrounding atmosphere or atmospheric pressure. So, we know that at sea level the atmospheric pressure is 760 torr. So, if I wanted to create the vacuum inside some chamber, so the pressure, if the atmospheric pressure is 760 torr, then the resultant pressure should be less than 760 torr. So, vacuum is a volume of space essentially empty of matter such that its gaseous pressure is much less than atmospheric pressure. Gaseous pressure of exactly 0 is only a philosophical concept and is never observed in practice. Quality of vacuum refers to how closely it approaches a perfect vacuum. So, when we say that it is a perfect vacuum, that means we consider that the effective density of gas molecule is almost 0, and how good is our experimental systems will be how good it will be close to a perfect vacuum. Vacuum became a valuable industrial tool in the 20th century with the introduction of incandescent light bulbs and vacuum tubes. Recent development of human spaceshift has raised interest in the impact of vacuum on human health and on the life forms in general. So, as we know that in the outer atmosphere, when we go to the space environment in the spacecraft, the pressure inside is different from the Earth's atmospheric pressure. So, what is the effect of this change of the pressure? So, that needs to be understood before sending some astronaut in the space. So, that is why the effect of the vacuum or low pressure on the human health is also another interesting area of the subject apart from the material science. Now, if you look at this, this diagram here, so here we are showing the different level of the vacuum. As you can see that when I say that the atmospheric pressure, it is something like 760 torr. Okay. So, 760 torr. Now, when I say about the low vacuum, so that means in a range of 10 to the power 2 or 10 to the power 1, like something like 10 torr. Medium vacuums, that goes from 10 to the power 0 to 10 to the power minus 3. 10 to the power minus 3 to 10 to the power minus 6, that is the high vacuum. 10 to the power minus 7 to 10 to the power minus 10 or even 10 to the power minus 9, that is very high vacuum, and anything beyond that, something like 10 to the power minus 10 to 10 to the power minus 17, 10 to the power minus 17 usually exist in the interstellar space. For the best lab vacuum, we make 10 to the power minus 12. So, this kind of and even like 10 to the power minus 11, that is the atmospheric pressure on moon. So, these are examples of the ultra high vacuum. So, in our solar cell devices, to make the metal electrode, we usually need the medium to the high vacuum. And one thing is obvious from this chart, that since the different level of the vacuum, the pressure is different. So, we need different instruments to create that vacuum, and obviously as we go to the high vacuum to very high to ultra high vacuum, we need more and more sophisticated instrument to create that kind of low pressure inside the system. So, let us learn about some common vacuum units we use in the system. There are many varied units that are used to specify pressure. The torr, the bar and the Pascal are commonly used. So, the most three commonly used unit for pressure is, one is torr, another is bar and another is the Pascal. Now, we will learn about what is the relation between them. But Pascal is the SI recommended unit for pressure, and so it is the best choice for the documentation. So, we as we know that we have the CGS system and SI system in addition to the APS system. In SI unit, and the Pascal is the pressure unit. So, very often we use the Pascal as a unit for the pressure, and it is the best method for the documentation of any kind of pressure. Now, atmospheric pressure, that is 760 mmHg. That means, if I take a mercury in a some kind of beaker, so 760 millimeter of the mercury, the amount of pressure it will exert, that is equal to the 1 atmospheric pressure. 760 mmHg, that is also called 1 bar, and 1 bar is equal to 10 to the power 5 Pascal. So, the atmospheric pressure is 1 bar or 10 to the power 5 Pascal. Now, another unit is torr. 1 torr is 1 mmHg. So, the atmospheric pressure is 760 mmHg. So, that means atmospheric pressure is 760 torr. 760 torr, that equal to 1 bar, that equal to 10 to the power 5 Pascal. 1 torr is equal to 1 by 760 of an atmosphere, and that is equal to 132 Pascal. 1 millitorr is 1 micromilligram weight of the mercury, and that is 0.13 Pascal. So, obviously 1 torr is 1 mmHg, or you need 760 torr to make 1 bar, or that is equal to the 10 to the power 5 Pascal, or 1 torr is 132 Pascal. So, 760 torr is equal to 760 into 132 Pascal. So, that is equal to 10 to the power 5 Pascal. 1 millibar is 1 by 1000 atmosphere, 0.76 torr is equal to 100 Pascal, and 1 Pascal is 7.6 millitorr is equal to 7.6 micro milli of pressure of the mercury. So, some of this important thing to remember is the atmospheric pressure, which is 760 mmHg or 760 torr, which is equal to 1 bar, which is equal to 10 to the power 5 Pascal. 1 torr is 132 Pascal. This two number is important to remember. Okay. Now, some of the like standard vacuum and how much vacuum they corresponds, that we will see it here. Vacuum or rotary vacuum, that correspond to 10 to the power minus 2 to 10 to the power minus 3 millibar or torr. So, 10 to the power minus 2 to 10 to the power minus 3 millibar, that is the vacuum created by the rotary vacuum or RUP pump. So, whatever the pump we use as a turbo pump in our daily life, that is also called RUP pump or the rotary vacuum pump. That kind of vacuum pump can create a pressure of 10 to the power minus 2 to 10 to the power minus 3 millibar or 10 to the power minus 2 to 10 to the power minus 3 torr. High vacuum is 10 to the power minus 3 to 10 to the power minus 7. So, 10 to the power minus 3 to 10 to the power minus 7 millibar, that is corresponds to the high vacuum. The rotary pump or the RUP pump will not be able to create that kind of vacuum. We need some another sophisticated vacuum pump to create that kind of vacuum. And then ultra high vacuum 10 to the power minus 7, 10 to the power minus 12 millibar or torr, that is the ultra high vacuum, and we need more sophisticated pumping instruments to create that kind of vacuum. So, we have classified the vacuum into 3 different category. One is the rotary vacuum, that is 10 to the power minus 2 to 10 to the power minus 3 millibar. Another is the high vacuum, that is 10 to the power minus 3 to 10 to the power minus 7 millibar, and another is the ultra high vacuum, that is 10 to the power minus 7 to 10 to the power minus 12 millibar. Okay, so now we have know what do we mean by the vacuum and why we need the vacuum. But next question is, how can we create the vacuum, or how can we create an environment where the pressure is much less than the atmospheric pressure. So, that is done by the instrument called vacuum pump. Now, in everyday life we have, all of us have seen some kind of vacuum pump, like when we use for sending the water from the ground floor to the first floor, or like when we use for the cultivation or agriculture the pump. So, that is also an example of a vacuum pump. But apart from that pump, there are also some other sophisticated pump which is required, like to for running instruments like STM, ACM, AFM, all these things. So, we will learn those things also. So, a vacuum pump is a device that removes gas molecule from a sealed volume in order to leave behind a partial vacuum. Vacuum pump was invented in 1650 by Otto von Guericke. So, it was invented long back 1650. Now, you look for some of the properties in a reduced pressure. So, for example, like if I take an atmospheric pressure which is 760 torr or 760 millibar, there the number density of the gas molecule is 2.7 10 to the power 25. Look at this number 10 to the power 25, and then the surface collision rate frequency is 3 into 10 to the power 27. So, the frequency between these two molecules is very, very high. So, if I wanted to deposit some let us say aluminum metal atoms on my solar cell. So, the aluminum vaporized atom has to suffer this many collision per unit length square per unit time before reaching to the target substrate. So, that is not a good case. So, that is why we need to rarefied the system, and the monolayer formation time is 3.3 into the power minus 9 second, and mean free path is 7 into 10 to the power minus 8 meter. Now, what is mean free path? It is the distance the atom can travel before it undergoes a collision. We will discuss that in details in the next few slides. Now, we come to about the Raab pump, which is 10 to the power minus 3 torr or 10 to the power minus 3 millibar. There the number density drastically reduced to 3.5 into 10 to the power 19. So, look here, it was 10 to the power 25, here it is 10 to the power 19. So, almost it is 5, 6, 7 order of magnitude difference. So, just by changing from the atmospheric pressure to the Raab vacuum, which is 10 to the power minus 3 millibar. So, we change the number density of the molecule to 7 order of magnitude, 10 to the power 25 to 10 to the power 19. What will be the consequence? The collision rate is now 4 into 10 to the power 21 per meter square per second. So, it is reduced, and mean free path is 0.05 meter there, and monolayer formation time is 2.5 into 10 to the power minus 3 second. So, it takes less time now. Now, you come to the high vacuum, which is 10 to the power minus 6 millibar, where the number density reduced further 10 to the power 16, 10 to the power 19 to 10 to the power 16, okay, and mean free path is 50 meter. And you come about the very high vacuum, which is 10 to the power minus 9 millibar, there the number density further reduced to 10 to the power 13. So, every case it is reducing by 3 order of magnitude from here to here, from here to here, okay, and mean free path is 50 to 10 to the power 3. Now, ultra high vacuum, which is 10 to the power minus 12, which is observed in the interstellar space or in the moon surface, there the number effective density of the gas molecule per unit volume per meter cube is 10 to the power 10, and the mean free path is 15 to the power 6. So, you look that as we come down with the pressure along this line from 760 to 10 to the power minus 3 to 10 to the power minus 6 to 10 to the power minus 9 to 10 to the power minus 12, the number density reduced from atmosphere 10 to the power 25 to 10 to the power 19, 7 order of magnitude, from 19 to 16, 3 order of magnitude, from 16 to 13 again 3 order of magnitude, from 13 to 10 again 3 order of magnitude. So, here any difference of the 3 order of pressure is also reflected as a 3 order of number density reduction, you can remember like this. And the similar effect we can observe the mean free path. If the number density reduced, then the molecules can travel more and more distance before undergo a collision. So, that is why you see the mean free path is increasing from 10 to the power minus 8 to 0.05 to 50 to 50 into 10 to the power 3 to 50 into 10 to the power 6. So, so the lesson is that starting from the atmospheric pressure, as we go from the Raab vacuum to medium vacuum to high vacuum, the effective number density of the gas molecule reduced and mean free path increase. So, the probability of collision also reduced, and the number of the gas molecule which stays in the systems, the residual number of the gas molecule which stays in the systems, that also reduced drastically. So, this slide actually explains why we need a vacuum more better way, because what we have learned that when you start from the atmosphere to go to more and more high vacuum. So, the two benefits we achieved, one is that the effective density of the gas molecule or the number of gas molecules per unit volume that reduced drastically, and consequently the mean free path increased drastically, and third thing is that the collision probability also decreased. So, it enhanced the probability of reaching the vaporized atom to the target substrate in a much better and much efficient way. So, that is the ultimate objective of going to the atmospheric pressure to the low vapor pressure, low pressure. Okay, so, now whenever we talk about any pump or whenever you will buy any pump, you will see that the manufacturer will provide you a graph like this, which is called a pump down curve. So, this pump down curve is actually a curve of pressure versus time, where in y axis we have plotted pressure in millibar and in x axis we have plotted time in second. It tells you what is the time scale required to reduce the pressure from a particular value to another certain value. So, whenever we like, let us say I have a chamber. So, of course, it will depends on the volume of the chamber, but if the volume of the chamber is standard and if I have a pump, so the capacity of the pump will depends upon how much time it will take to reduce a number density of the gas molecule to a particular value, and that is called the pump down curve for that particular pump. Okay. So, in the case of the volume depositions, so you can see that the pump down curves, like the time required is 10 to the power 1, but as we go, like things like surface diffusions. So, coming from something like 10 to the power minus 1, let us say, or even less than that, 10 to the power minus 2, let us say, from this pressure to come down to 10 to the power something like 10 to the power minus 9, if I consider about the surface depositions, and if this is 10 to the power minus 9 and if this is 10 to the power minus 3. So, I go from a time scale of 10 to the power 3 to 10 to the power somewhat around 8, but the volume depositions, that is very rapid, very fast. If you go to the diffusion, the kinetics is much slower. If you go to the permeation, it is almost saturated. So, the meaning of this curve is that if you go from a volume deposition to a surface deposition to the diffusion to the permeation, kinetics becomes much slower, and that is expected. So, it is much easier to deposit on the volume rather than depositing on the inner surface. So, that is why kinetically one process is much favorable than the other, provided other constants of the parameters remains constant, and that gives you an idea, like if I have a pump, I know this much amount of time it will take to deposit a particular material, and if that is not deposited in that by the particular time, so we know that there is a problem in the pump. Okay, the classical kinetic theory is known to many of us, but if we just want to revisit that in the context of the low pressure, then we can understand the idea behind this mean free path. The particles of gas molecules are moving randomly, each with a unique velocity, but following the Maxwell-Boltzmann distributions. And what is Maxwell-Boltzmann distribution? We know that there are 3 different distributions. One is the classical distribution, Maxwell-Boltzmann distribution, and another 2 is the quantum distribution. One is Fermi-Dirac statistics, and another is the Bose-Einstein distributions. Now, the Maxwell-Boltzmann distribution, which is obeyed by most of these macro systems, that is given by the Fv, or the probability with a of velocity v, that is equal to m by 2 pi kt to the power whole 3 by 2 into e to the power minus mv square by 2 kt. That we have learned from the Maxwell-Boltzmann theory. Okay. This is the particle of a gas when it is moving randomly to the probability of having it with a velocity v. So, from this one, if we integrate it and we get the average speed v bar is equal to 8 kt by pi m to the power whole half. Okay. So, where k is the Boltzmann constant, T is the temperature, and m is the mass of the gas molecule. Now, with the molecular weight of the air around 29 gram per mole, considering that the air has 75% nitrogen and 25% oxygen, where the molecular weight of the nitrogen is 14 into 228, and for that for oxygen is 16 into 232. If we consider that, and if we consider the weight percentage out that, what it will comes out, the weight of the air is 29 gram per mole. So, that means 1 mole of air weigh 29 gram at the room temperature. So, if we consider that, the value of m comes out to be 29 into 1.67 into the power minus 27 kg. So, if you substitute the value of m like that and the temperature 293 Kelvin and value of the Boltzmann constant, then the average speed comes out like 461 meter per second. Now, same ballpark as the speed of sound. What is the speed of sound? 345 meter per second. So, this is little bit higher than the speed of sound. So, the average speed of the gas, average speed of any gas of the in the normal air, considering the room temperature and the average molecular weight of the air as 29 gram per mole, is very close to that for the speed of the sound in the air. So, the mean free path is the typical distance travelled before colliding with another air molecule. So, as we have defined earlier also, it is the distance the molecule can travel before it suffer collision with another neighboring molecule. Treat molecule as sphere with radius r. So, consider that every molecule is now a sphere which has a radius of r. If the center of another molecule comes within 2r of the path of a select molecule, now if I have to collide this molecule with another gas molecule which is also has a radius of r, so when they have to collide, then basically both of them has to come face to face. So, that means this sphere has to come now like this, So, in that case, so the effective radius then will be r plus r, that is 2r, and that is why when the center of the another molecules comes within a distance scales of 2r, then a molecule can undergoes a collision with the another molecule. So, now when you are considering it as a 2r as the effective the distance between the two center, so then each molecules will sweeps out a cylinder of volume 4 pi r square V t, right. So, now you can consider that there is a cylinder like that, the cylinder of volume. What will be the cylinder of the volume? This is the area of this circle times this distance. Now, what is the area? Pi into 2 r square, because now this is the effective distance for the collision to happens. Now, 2 r square is 4 r square. So, this is 4 pi r square, that is the area of the base. Now, if the area of the base, that is the two molecule has to come close together. So, that we got this area. Now, to get a cylinder volume, I have to multiply the base area along with the height. Now, what is the height? Now, this gas molecule which is we have considered as a sphere, they are moving with a velocity v. So, at time t, if they come close to each other, then the distance they can travel is v into t. So, that the length scale, this z length, that is equal to v into t. So, that is why the volume v is pi into 2 r square into v into t. So, that is what this is 4 pi r square v into t, that is why it is written here 4 pi r square into v into t, the volume of the sphere. So, each molecule sweeps a cylinder of volume 4 pi r square v t in time t at velocity v. Now, if the volume density of the air molecule is n, the number of collision in time t, how many collision it will do if there are n number of molecules in unit volume. So, obviously it will be 4 pi r square v t into n, because now each molecule will sweeps out a cylinder of volume 4 pi r square v t, and there are n number of molecules per each volume. So, the collision probability in time t, it will be the volume of the cylinder times the number of the molecules available in that cylinder. So, that is 4 pi n r square v t in. So, that is the volume times the number of molecules per unit volume. So, now we have considered so far the average speed. Now, correcting for the relative molecular speed, because now the both of the molecule is moving each other. So, we have to consider the relative molecular speed. So, we can express the collision per unit time. We have now z is equal to 4 root 2 pi n r square v. So, basically if we consider the relative motion between the two gas molecules, so the 4 factor will be replaced by 4 root 2. So, that is what instead of 4 we have written 4 root 2, and the pi is like pi, and n is n, r square is r square, and v comes like v, and then we have the t also. But if we consider the unit time, then t goes out. So, per unit time the collision probability or the collision per unit time, it will be 4 root 2 pi n r square v. Now, that we have the collision frequency, that is the number of collisions per unit time. What is that? That is the collision frequency. So, that is z. So, now we can have the collision frequency. So, we can get the average distance between the collision. So, average distance between the two collision is lambda. If you define as lambda, that is v by z. Why v by z? Because at unit time, let us say at unit second, at 1 second, the molecule can travel this much distance, and while traveling this distance in this time scale, this 1 second, it can undergoes z number of collision. So, what is the average distance then they can travel before they suffer the collision? So, let us say, so one molecule, and this distance is v, there is one molecule here, another molecule is here. So, one molecule travels from here to here, and the distance between the two molecule is v, and between these two distance the number of collision that can happen is z. So, what is the probability or what is the average distance between the two collision? Obviously, that is v by z. So, that is what it is defined here, the lambda or the average distance between the collisions is v by z. Now, we have already found out an expression of the z. So, if we plug in the value of z as 4 root 2 pi n r square v, so v and v cancels out, giving that lambda is equal to 1 over 4 root 2 pi n r square. So, for air molecules, the value of this r radius is 1.75 in 10 to the power minus 10 meter, that we have learned. So, if we consider the value of r like that, so the value of lambda comes out as 6.8 in 10 to the power minus 8 meter or 68 nanometer at atmospheric pressure. And this lambda is called the mean free path, because it is the average distance the molecule can travel before it undergoes a collision. And you note that this average distance the molecule can travel before it undergoes a collision, or like the mean free path, that is inversely proportional to the number density n. So, lambda is inversely proportional to the number density n, which is itself proportional to the pressure. So, the mean free path is inversely proportional to the number density, as you have learned from this equation. Now, number density or the number of gas molecule in a particular volume, that will depends upon the pressure. Now, we have learned that from one of our earlier chart. If we go back, okay, so you have seen here, if we go back to the pressure from 10 to the 5 to 19 to 10 to the power 16, 10 to the power 13 to 10 to the power 10. So, as the pressure is reducing, the number density is reducing. So, number density depending on the pressure. So, since the mean free path is inversely proportional to the number density, that means the number density will be lower, mean free path will be higher. Now, if I go to the low and low pressure, or if I go from the low to high vacuum, the number density reduced, that is why the mean free path increase. Now, when we read about this chart, we have talked about that there are 3 important parameters to note. When you reduce the atmospheric pressure to the high vacuum, to very high vacuum, to ultra high vacuum, what you have observed, the number density of the gas molecule reduced, but consequently the mean free path increase, and this explains the reason, because the mean free path is inversely proportional to the number density. Now, when we reduce the pressure, since the pressure reduction leads to the reduction of the number density, that is why it leads to the increase of the mean free path. Okay. So, we can make a rule that lambda is equal to 5 centimeter by p in millitorr. So, if we put the values of the lambda in terms of the p, we can also get an expression that lambda is equal to 5 centimeter by p in millitorr. But what is important is that here the mean free path expression, starting from a Maxwell-Boltzmann statistics, we can derive an expression for the mean free path, which is inversely proportional to the number density of the gas molecule, which is again dependent upon the pressure of the gas molecule, or which is proportional to the pressure of the gas molecule, and that is why mean free path is inversely proportional to the pressure. As you reduce the pressure, mean free path will increase, and vice versa. If you wanted to put in terms of the pressure, so lambda is inversely proportional to the pressure, or by doing putting some numbers, arbitrary numbers for the air molecule at the normal standard atmospheric pressure, we can get a value lambda is equal to 5 centimeter by p in millitorr. So, then what is the relevance of the mean free path? Mean free path is related to the thermal conduction of the air. If the mean free path is shorter than distance from the hot to cold surface, there is a collisional or conductive heat path between the two. Once the mean free path is comparable to the size of the vessel, the paths are ballistic. Collision ceases to be important. Though not related in a 1:1 way, one can also cares about transition from the bulk behavior to molecular behavior. Above 100 meter torr, so which is equivalent to 0.3013 atmosphere, air is still collisionally dominated, that is viscous, and lambda is about 0.5 millimeter at this point. Below 100 millitorr, gas is molecular and flow is statistical rather than viscous. Bulk is no longer pushes on bulk air. So, basically what it gives rise, like the mean free path idea, that leads to the concept of the molecular conductions in the air. So, based on the molecular conduction, we can define the conduction either as a viscous flow or as a molecular flow. In a viscous flow, like which is shown in this block, a momentum transfer happens between molecule, whereas in a molecular flow, molecules moves independently. Okay. So, in a viscous flow, so the collision probability is much higher, as you can see here the number of molecules is higher. So, that there is so when the one molecules collide with another, there will be a momentum transfer between molecules, but here the molecules move independently, there will be no momentum transfer between this molecular flow. Now, we will be looking for a region where the transition happens from the viscous flow to the molecular flow. So, the viscous flow, the distance between molecules is small, collision between molecule dominates and flow through momentum transfer. So, there are 3 parts in it. First, in a viscous flow, the distance between the molecule is small, collision dominates and flow happens through the momentum transfer, and in this case pressure is usually greater than 0.1 millibar. On the other hand, molecular flow, distance between molecule is large, collision between molecules and the wall dominate. So, in the previous case you can see that the collision between the 2 molecules is dominating. So, the one molecule can transfer momentum to the another molecule, but here collision between the molecule and the walls dominate. So, the molecule does not transfer the momentum to the neighboring molecule, but it rather collides with the wall. So, here the distance between the molecules is large and collision between molecules and wall dominate and flow through random motion, not through the momentum transfer, and it usually happens for a pressure smaller than 10 millibar. So, it is happening greater than 0.1 millibar, P greater than 0.1 millibar, and here P is smaller than 10 millibar. So, what is the region then in between 0.1 millibar to 10 millibar? That is our transition region, transition flow, where the region between the viscous flow and molecular flow. So, when the pressure is between 0.1 millibar to 10 millibar, that defines the transition flow regions. So, we consider that, like what will be the molecular density and mean free path when this pressure changes. For an atmospheric pressure, like the number density or the molecular density is 3 into 10 to the power 19. But when you go to 10 to the power minus 3 millibar, it is 4 into 10 to the power 13, and when you go to 10 to the power minus 9 millibar, it is 10 to the power 7. And mean free path, as you have learned that in the case of the atmospheric pressure, it is 10 to the power minus 6 inch or 10 to the power minus 5 millimeter. When we change the pressure to 10 to the power minus 3 millibar, it is 5.1 centimeter, increased drastically. When you reduce the pressure more 10 to the power minus 9 millibar, it is increased more and more to 50 kilometer. So, as we change the pressure or as we decrease the pressure, number density of the gas molecule decrease and consequently mean free path increase significantly. So, we can define the flow regions also by a quality factors. So, for example, for the viscous flow, we can define the mean free path divided by the characteristic dimension is less than 0.01. So, if we take a ratio of the mean free path by the characteristic dimension, if it is less than 0.01, then it defines a viscous flow, and if the value is greater than 1, then this is a molecular flow, and between 0.01 and 1, that is a region for the transition flow. So, whenever we look for whether it is a viscous flow or whether it is a molecular flow, basically we need to know the mean free path of the system and we need to know the characteristic dimension, and we need to take a ratio of the mean free path to the characteristic dimension. If it is less than 0.01, then it is a viscous flow. If it is greater than 1, then it is a molecular flow. If it is in between 0.01 and 1, then it is a transition flow. Now, what is conductance in viscous flow? Under viscous flow conditions, doubling the pipe diameter increase the conduction 16 times. Well, I mean one important thing to know here, that why we are talking about the mean free path. Is it only that it is lessen with the pressure? No, actually the mean free path changes whether the flow is viscous flow or a molecular flow. But what is the important for that? This viscous flow or the molecular flow is directly related to the conductance, and that is we are all interested about. Under viscous flow condition, doubling the pipe diameter. So, this is the diameter, right. So, if you double the diameter of the pipe, that increase the conductance 16 times. So, the conductance is inversely related to the pipe length. So, if you increase the diameter d to 2d, so the conductance, if it is d, now it is 16 C, and the conductance is inversely proportional to the length of the pipe. So, this is a condition under the viscous flow, but the molecular flow it will be different. Actually, these all things we required in concern to the vacuum gadgets. When we talk about the vacuum gadgets and the piping and all these things, so these concepts will be very, very important. Now, there is an equation, we are not deriving it here, we can write the conductance or what will be the flow of the gas molecule per unit time, or how good the flow is, that we define in terms of with the conductance. Under the viscous flow, if we consider a long round tube, so the conductance is given by 1.38 into 10 to the power 2 d to the power 4 by I into P1 plus P2 by 2 liter per second. Okay. Here d is the diameter of the tube in centimeter, L is the length of the tube in centimeter, L is the length of the tube, P1 is the inlet pressure and P2 is the exit pressure. So, basically if I have a long round cube like this, long round tube like this, okay, and the diameter here is d and the length is L. So, the conductance inside this tube is proportional to the d to the power 4, inversely proportional to the length, and it depends upon the pressure P1 at the inlet and pressure P2 at the outlet. So, P1 plus P2 by 2. So, it is d to the power 4 divided by L into P1 plus P2 by 2, this amount of centimeter per second. But if you go to the molecular flow, it will be different. Conductance in a molecular flow, it is given by 3.81 into d to the d cube divided by L into square root of T by m. So, under molecular flow condition, doubling the pipe diameter increase the conductance 8 times, not the 16 times under viscous flow, and the conductance is inversely relation to the pipe length. So, one thing is common both in viscous flow and molecular flow. So, it is if we increase the diameter of the pipe, conductance increase significantly. So, that is expected, right. So, if we have a smaller diameter pipe, and let us say if I have a very larger diameter pipe. So, and if I passing the water through both of this pipe, a narrow pipe and a very large pipe. So, in which case you expect to have a more amount of water to pass, of course in a larger diameter pipe. So, that is why the conductance in a larger diameter pipe is higher than a narrower diameter pipe, and the dependence on the diameter is 16 times or d to the power 4 in the case of the viscous flow, and it is d cube in the case of the molecular flow. And in both of these cases it is inversely proportional to the length, and that is also expected. Let us say I wanted to pass the water through a pipe, through a water pipe. Now, I have a 10 centimeter pipe and I have a 10 meter pipe. Now, in which case I will expect that the flow is more favorable. Of course, in a smaller length pipe the flow will be more uniform and more favorable than a longer length pipe. So, that is why it is inversely proportional, conductance is inversely proportional to the length, you can remember like that. But in the case of the molecular flow, it also depends upon the temperature and the mass, atomic mass unit. So, in addition to d cube by I, it also depends, here d is the diameter of the tube in centimeter, L is the length of the tube in centimeter, and T, that is the temperature in Kelvin, and M is the atomic mass unit. This is the molecular mass which is expressed in atomic mass unit. So, basically what we have learned that if we go from the atmospheric pressure to the lower pressure, like if we go to the roughing pump, if we use the rough pump, if we go to the rotary vacuum something like 10 to the power minus 2 millibar, or if we go to medium vacuum or like high vacuum or ultra high vacuum. So, the number density of the gas molecule reduced drastically, mean free path increase. We have derived an expression for the mean free path, and we have seen that mean free path is inversely proportional to the pressure, and as the mean free path changes, considering the characteristic dimension, we can define a quality factor which gives the flow is viscous or molecular or in a transition region, right. And if the flow is viscous or the molecular, conductance will be different. And now the conductance in a viscous flow and the molecular flow, it depends upon the diameter and the length of the pipe, and that all actually is important to understand when we are talking about the vacuum gadget subsequently. So, in today's lecture we have learnt about why we need to create the vacuum and what are the different concepts related to the vacuum, but what is important to know right now, how we can create the vacuum. So, we know that we need a pump to create the vacuum, but in the next lecture we will learn about the different kind of pumps and the different kind of pumps how they can create the vacuum. Okay? Thank you so much.